All right, let's look at the proportionality theorems, and I actually want to prove to you using some algebra. I think this is a good review of algebra. And so let's take a look. If we have a triangle and we draw any parallel line, right? It could have been there or there or there or there. What we for sure know that the theorem's going to say is that that parallel line divides the two sides proportional. Okay? And so this is to this as this is to that. And I want to show you that it's the same thing as saying that the two triangles are similar. Okay, so let's discuss. Are the two triangles similar? And that means little triangle and big triangle. Again, not triangle and trapezoid. Little triangle, big triangle. And so if you think about it, if these things are parallel, then that angle and that angle are the same, and that angle and that angle are the same, and both the little and the big triangle share that one. So what I'm telling you is that for sure, this triangle is similar to the big triangle. Okay, we already know that. And I want to prove to you that knowing this actually leads us to the proportionality theorem, which is really nice. Okay, and I want to show you the algebra here. I'm going to label these all letters, and I want to show you that it works. Okay, so let's just label this little a, little b, little c, little d. Okay, so that would make this triangle BC, and that would make this distance a plus b, and it would make this distance c plus d. Okay, and I want to use this fact to then prove to you the proportionality theorem. So let's go over here and let's not assume we know that at all. What we know is that these two triangles are for sure similar because I proved to you they have angle, angle, angle. So because they're similar, their sides are in proportion. So what we know is that b is to a plus b, just as c is to c plus d. That's a fact of similarity. The ratio of these two sides is equal to the ratio of those two sides. And let's work with this algebra. So I would multiply both sides by a plus b, meaning this is division, and it's going to go over here with multiplication, and c plus d is going to come over here. So I'm going to have b times c plus d, and on the right side I'm going to have my c times a plus b. Okay, so I multiply this out and I get BC plus BD equals CA plus CB. Okay, and I want you to notice that both sides of the equation have BC and CB on it. Remember, 3 times 4 is the same thing as 4 times 3. So I can subtract both sides by that and I can cancel that. And I'm left with BD equals CA. And what I can do is I can divide this side by A, and I can divide this side by D, and I can get this. And this is saying that the triangles are similar, and this guy is saying the proportionality theorem. The proportionality theorem is derived from similar triangles. The proportionality theorem says that any parallel line will proportionally divide each of the sides. So B is to A as C is to D. Okay, let's do a concrete example of this. And I'm going to take the same picture. So let's say something like that. And I'm just going to make up some numbers, so just bear with me. They might not look exact. Let's say that's 2, and that's 3, and then that's 10. Okay? And this is x. We don't know it. Well, I'm telling you that if you know these are parallel, the parallel side divides the side proportionally, meaning if this piece is 2 and this piece is 10, this piece is 5 times bigger than that piece, then x is 5 times bigger than 3, and so x has to equal 15. And I'm telling you that the proportionality concept comes from similar triangles. I just proved it to you right here, that no matter what A, B, C, and D are, a parallel line will form similar triangles. Similar triangles will cause the sides to be broken up proportionally, and that's what the proportionality theorem says. So we can have triangles like this, where once you know these parts, then you know that part for sure. It's whatever scale factors here to here is the same scale factor here to here. The sides are broken up proportionally. And if you look at similar triangles here, the little triangle would be 2, the big triangle side would be 12, this would be 3, and the big thing would be 18. And look, that's the same thing. 2 is to 12 as 3 is to 18, check. Right, that 15 makes sense in terms of solving it. 2 is to 10 as 3 is to 15. 2 is to 12 as 3 is to 18. So again, these two actually imply the same things. We see triangles like this. We could see it the picture like this, which is that's pretty cool. So the hypotenuses, but again, the hypotenuses break it up into pieces. So like if this is 4, and this is 2, and this is 6, what does that have to be? If this piece is twice, or excuse me, if this piece is half of this, then this piece is half of that. For sure, then that's got to be 3. Has to be. And again, you can look at any of those ratios and prove that that's 3. You can also look at ones like this. Anywhere you want, draw another height. So I could put it here, I could put it there, I could put it there. Drop another one. Right? This piece compared to this piece, if that's 2 and that's 8, doesn't matter. If that's 2 and that's 8 and this piece is 4 times bigger than that piece, then this is 4 times bigger than this piece. So if that's 8 and that's 6, this is 1.5. It has to be. These ratios, the pieces are in the same ratio because parallel lines, those would be parallel. Parallel lines proportionally break up the side, meaning the side pieces themselves are in proportion. 8 is to 2 is 6 is to 1.5. 4 is to 2 is 3 is to 6. 2 is to 10 is 3 is to 15. Again, as long as these things are parallel, and these are your main 3 pictures, right? So it looks like a kind of an acute a pyramid, and we draw a parallel line. It can be a right triangle, and I can draw another hypotenuse parallel, or I can draw a right triangle and draw another altitude or height parallel. Those are your 3 main cases. But the big thing is that this is true. This is true, and I showed that it's true because the triangles are similar, because parallel lines make them similar. So the proportionality thing isn't really a new concept. It just is derived from similar triangles. But it is actually very helpful in how fast we can do certain things because we know that the sides have to be broken up in proportion. Okay? And again, you're going to do problems where there's like x's here and y's there. And again, I could have put a y there, and I could have said, oh, y is equal to 3. And again, I could have made that a z, and you could have said z is 1.5. And you can set up the proportions if you want to. You know, let's say you didn't know that, and that was x. You could have just said 8 is to 2 as 6 is to x, right? And you multiply and get 8x equals 12, x equals 12 eighths, which is the same thing as 3 halves, which is the same thing as 1.5. All of those things would have worked. Okay, so hopefully this kind of gets you started on proportionality theorems.